Since we've recorded history, mankind has recorded his thoughts and observations on the heavens in the form of astrology or astronomy. Until the 18th century, there was no dividing line between the two. In the 1700s, astronomers decided that astrology had no basis in science. This presentation is meant to convince astronomers that astrology indeed has a basis in science that amazingly enough can be proven using Einstein's theory of relativity. In Einstein's theory of relativity, if an object leaves Earth and accelerates to a speed nearing the speed of light, its gravity and mass density will increase. If that object slowed back down to Earth's speed again, then obviously its gravity and mass density would return to Earth's standards again. So if an object is accelerated towards the speed of light, its gravity and mass density increase. If it slows back down again, its gravity and mass density decrease. And according to relativity, the expansion and compression of mass, gravity, and time only takes place in a small window very close to the speed of light. If a change in velocity occurs below this critical window of velocity, there is no change in gravity or mass density. So what if one day we realized that gravity and mass density increased and decreased with changes in velocity as subtle as the Earth's orbital speed? Only we didn't realize it because time changed in direct opposite proportion. This could only lead us to one possible conclusion, and that is that the Earth, the Sun, the galaxy, the entire universe, everything that we see, is all traveling at the same relative speed and direction in that little window of velocity near the speed of light. Let's consider the Earth's orbit around the Sun as it travels through space. On one leg of its orbit, the Earth is traveling 67,000 miles an hour faster than the Sun. On the opposite leg, it's traveling 67,000 miles an hour slower. Later in this presentation, I'll offer 10 points that indicate that this small variation in speed causes a significant variation in the Earth's gravity and mass density. But for now, based on this perspective, I'd like to show you how relativity validates astrology. Since the dawn of history, civilizations like the Mayans, the Chinese, and the Europeans have made a science out of documenting the correlation between historical events and the alignment of the planets. They've reflected on these records as a means of predicting future events. These civilizations also believed that the time of year that a person was born had a bearing on their personality. When you consider that the Earth's gravity, mass density, magnetic fields, and everything that's measured by time vary with the Earth's orbital speed, then you might consider that these factors do have a bearing on people's character that are born different times of the year. So what physical influence would the alignment of the planets have on Earth? Everyone knows that the Moon orbits the Earth, but not everybody knows that the Earth also orbits the Moon. Of their combined orbital mass, the Earth makes up 85% and the Moon 15%. 85% of the orbiting that we see is on the part of the Moon, but 15% is on the part of the Earth. As the Earth orbits the Sun, it's gently pulled side to side and forward and back by this interaction with the Moon. Since gravity and mass density are affected by velocity, this does have a small effect on the Earth's gravity and mass density. The reason I bring this up is that the Sun and the planets in our solar system also orbit each other. As the planets align in different directions, they gently pull the Sun side to side and forward and back as it travels in its galactic orbit. This subtle variation in the Sun's velocity causes its gravity and mass density to vary in direct proportion. This slight variation in the Sun's properties could very well be responsible for long-term weather changes. For thousands of years, astrologers have made projections of feast and famine based on the alignment of the planets. The people at Farmer's Almanac still do. But until the theory of relativity is considered, there was no scientific explanation as to why it worked. I'm about to give 10 different examples of how relatively small changes in velocity cause very significant changes in gravity and mass density. A good place to look for evidence of this would be to observe the Earth's gravity as it orbits the Sun. The Earth's orbital speed is 66,000 miles per hour, which means that during the September equinox, the Earth is traveling 66,000 miles an hour faster than the Sun, while during the March equinox, the Earth is traveling 66,000 miles an hour slower than the Sun. This is a total variation in speed of 132,000 miles per hour. Would 132,000 miles an hour cause a perceptible difference in the Earth's gravity and mass density? Indeed it would. It would be perceptible from a static point of zero velocity, or even from the Sun, but it would not be perceptible from Earth. Even if the Earth's gravity doubled at its peak velocity during the September equinox, we'd never notice, because as gravity and mass density increase, time slows in direct proportion. So 2 Gs experienced in half the time is still exactly 1 G. We can observe that the Earth's gravity oscillates relative to its orbital speed if we consider the Earth's gravitational relationship to the Sun. Consider that the Sun's velocity and gravity are constant relative to Earth's. If the Earth's gravity indeed oscillates with its orbital speed, then we could expect to see that reflected in its orbital path. The faster the Earth travels, the closer its orbital path would be to the Sun. The slower it travels, the further the orbital path. As it turns out, the Earth does travel this offset elliptical orbital path, along with every other satellite in the universe. So this is an indicator that relativity has something to do with the orbit of all satellites. There's another indicator that the Earth's gravity increases and decreases with its orbital speed, and that would be reflected in the tides. During the September equinox, the Earth is reaching its highest orbital speed of the year, which means the Moon is also traveling its highest speed of the year. The tides result from the Moon's gravity, and if gravity is indeed proportionate to velocity, then at this time of the year, the Moon's gravity should be at its peak, as well as the height of the tide. The September equinox is the point at which the Earth's gravity reaches its peak, but it's not necessarily the point at which the Moon reaches its gravitational peak. It's not until the Moon comes into alignment with the Earth and Sun, to where all three are traveling in the same direction, that the Moon reaches its gravitational peak. Tidal records can verify that the Moon's gravity reaches its height at the exact time of year where the Moon's orbital velocity reaches its height. This is a model created by the National Oceanic and Atmospheric Administration that shows predicted annual tide cycles. They averaged out the tidal activity that took place between 1930 and 2006. In averaging out tidal activities over 76 years, not only did they eliminate earthly effects on the tides like weather, but also they averaged out the position of the Moon relative to the Earth during the September equinox. The annual tides reach their peak squarely on the September equinox. This chart isn't just a record of the tides. It's also a gravitational footprint, a record of the Earth's fluctuating gravity. This gravitational footprint left behind in the Earth's tides does not just belong to the Earth and its orbit around the Sun. This is a universal gravitational footprint that applies to all satellites everywhere. That being the case, then the gravitational footprint that the Moon leaves behind in one monthly orbit should be the same as the gravitational footprint left behind by the Earth in one annual orbit. And as you can see, it's a match, which verifies that a satellite's gravity oscillates proportionate to its orbital speed. A pulsar is at least two stars that are locked in each other's orbit as they race through space. One star is continually catapulted ahead, while the other is continually falling behind. As the stars' velocities oscillate, we can see evidence that their gravity and mass density are oscillating as well, all the way from Earth. There's something else that we can see with our own eyes that would verify that the Earth's gravity increases with its velocity. If the Earth's gravity is indeed at its peak during the September equinox, then the Earth's gravity is reaching further out into space than it is any other time of the year. In the months that followed, we'd see, as a consequence of this increased gravity, an increase in meteor activity. And as it turns out, the most spectacular meteor showers of the year take place during this time period. Next, let's consider the heat and light that we receive from the sun. On the 1st of January, the Earth is 3 million miles closer to the sun than it is on the 1st of July. Oddly enough, the Earth's average temperature is 3 degrees cooler in January when it's closest to the sun. There's one logical explanation for this. Time oscillates relative to orbital speed, the same as gravity and mass density. So the Earth receives more heat and light per second from the sun during the summer than it does in winter. It was the search for the answer to the following question that led me to this entire realization about relativity. How is the inertia that satellites lose to centrifugal force replenished? In order for a satellite to enjoy the zero-G status it needs to maintain an orbit, the gravity it's experiencing must be equally countered with centrifugal force. The problem is centrifugal force is not free. Centrifugal force is a deflection, a circular deflection. If an object in motion isn't influenced by any type of deflection, then it'll continue moving in a straight line forever. When an object in motion is deflected by another object, it loses part of its inertia to the object that deflected it. As far as deflection goes, let's say an object that was under 1g of acceleration became deflected by an immovable barrier. If that object were still under 1g of acceleration, which is 32.2 feet per second, then at the end of 1 second, it would not have moved 32.2 feet. In fact, it would not have moved at all. The barrier would have absorbed the entire g of acceleration. If an object under 1g of acceleration were forced into a circular path by an axis, and it traveled 32.2 feet in the period of 1 second, winding up exactly where it was 1 second before, it would be just like the previous example, to where the deflection absorbed the entire g of acceleration. And whether that barrier is an inside axis or an outside race, it is absorbing the acceleration and inertia from the object that it's deflecting. I'm saying that centrifugal force costs inertia, and you're probably thinking, if that's so, how can a flywheel be such a practical way to store inertia? If you counterbalance your deflected object with a like object, you eliminate centrifugal force. So if the first object is pulling on the axis with 1g of deflection, the opposing object will counter that and create a 0g deflection. To see this principle in effect, you only need to go as far as your washing machine. This is an example of an evenly balanced load on a spin cycle. But if you shift the load to one side, eliminating the counterbalance, the same machine with the same load and motor can barely spin at all. A satellite in orbit does not have a counterbalance, so therefore it does lose its inertia to centrifugal force. I couldn't help but wonder what mystical process replaced this lost inertia. I could only think of one logical answer to this question, that a satellite's gravity oscillates relative to its orbital speed. This meant that the principles of relativity were evident at much lower speeds than anyone had imagined. Just like with a ball on a string, oscillating gravity continually whips satellites around in their orbit. With each orbit, the oscillating gravity replenishes the inertia lost to centrifugal force. If you stop this whipping action, then it's not long at all before the satellite loses its orbit. So the concept that a satellite's gravity oscillates relative to its orbital speed would explain why satellites don't lose their inertia to centrifugal force. The next question that came to my mind was what would happen if you launched a satellite into such an orbit that its velocity did not oscillate relative to our solar systems. If gravity is indeed proportionate to velocity, then that whipping action that keeps satellites in orbit would be gone in this case. There is one kind of orbit that does not create oscillating velocity relative to the velocity of our solar system. If you launched a satellite into a polar orbit, as long as it was traveling to and fro in the same direction as our solar system, you'd have the same oscillating velocity and therefore gravity as an equatorial orbit. But if a satellite were in a polar orbit, not orbiting for or against the direction of the solar system, then it would lose that oscillating velocity and gravity. Just like that ball whipping on a string, the satellite would soon lose its orbit. I did a little homework and I found out that it's a bit of a mystery as to why polar orbits are such a hit-or-miss proposition. The inconsistency of polar orbits just serves to further reinforce the concept that gravity does oscillate with orbital speed. If relativity is responsible for oscillating gravity in satellites, it's also responsible for long-term weather changes. And once we see why, we can predict future long-term weather changes. It has a lot to do with orbit wobble. The Earth and Moon actually orbit each other. Of their total orbital mass, the Earth is 85% and the Moon is 15%. So 85% of the orbiting that we see is on the part of the Moon, but 15% is on the part of the Earth. So on the Earth's orbital path around the Sun, the Moon's pulling it gently forward and back and side to side, which affects the Earth's gravity and mass density slightly. The reason I bring this up is that as the planets in our solar system orbit our Sun, they also pull it forward and back and side to side. The intensity of that wobble depends on the alignment of the planets. And as the Sun's velocity fluctuates as a result, so does the velocity of the entire solar system, including Earth. We saw that the Earth's average temperature changed over the course of a year as a result of its orbital velocity. You can bet that with the changing speed of the entire solar system, that those weather changes would be more significant and longer lasting. So if the Earth's average annual temperature varies by 3 degrees as a result of its orbital speed, and we experience long-term weather changes because of the influence the planets have on the Sun's velocity, then imagine the influence that the galaxy's orbital speed has on the Earth. As our solar system reaches its peak velocity in its galactic orbit, its gravity and mass density will also reach their peak. And when our solar system was traveling in the opposite direction from the galaxy, its gravity and mass density would be at their lowest point. It's like having the 4 galactic seasons of summer, fall, winter, and spring. During the galactic winter, imagine what the effects would be of having a dramatically lower gravity and mass density. If this occurred, we could expect that the inhabitants of Earth could grow to much larger sizes. Although these larger creatures would enjoy agility from the lower gravity, it's likely that their lungs would also be larger to breathe the thinner air. And then as our solar system swung into the galactic spring, our gravity and mass density would begin to increase. As the Earth's gravity increased, it's likely that these large creatures wouldn't be able to stand under their own weight. Those that survived might have done so by spending all or part of their time in the zero buoyancy of water. Then as our solar system swings into its galactic summer, the Earth's time, gravity, and mass density all intensify. It's likely that this would be the time that all organic sediment would be compressed into coal and oil. The tectonic plates would be more mobile, and new mountain ranges would be formed. It's also likely that if we looked at the sediment from this period of time, that because of the Earth's increased gravity, we'd see a lot more cosmic debris, like iridium. I'm saving the best for last. Mars offers the most conclusive evidence yet that relativity governs time and everything that's measured by it at low orbital speeds. It's very evident by Mars's massive water erosion that it's recently experienced rain, lots of rain. Right now, the barometric pressure of Mars's atmosphere is equal to Earth's atmosphere at 100,000 feet. At that barometric pressure, water would instantly vaporize. There's just no way that it could rain. But it has rained recently on Mars, and judging by the lack of impact craters in the areas that have been affected by water erosion, it looks like it was a fairly recent occurrence. In order for rain to even be possible, the circumstances have to be just right. Here on Earth, with a barometric pressure of 29.9 inches of mercury, it has to be between 32 degrees Fahrenheit and 212 degrees Fahrenheit for water to even exist in its liquid form. So not too long ago, Mars must have had an atmosphere that was very similar to ours, both in temperature and barometric pressure. In order to support an Earth-like rain-bearing atmosphere, Mars would have to have an Earth-like gravity, which means its gravity would have to increase nearly twofold. At the peak of our galactic summer, not only would the gravity on Mars reach its peak, but the light and heat received from the sun would increase in the same proportion. These were the first 10 things I could think of that would either prove or disprove the concept that relativity is not only evident, but essential in the low-speed orbit of satellites. To recap those 10 points, 1. It would explain pulsars. 2. It would explain the offset elliptical orbit of all satellites. 3. It's indicated in the tidal records of both the Moon and Earth. 4. Meteor showers are the most spectacular when the Earth is at its highest orbital speed. 5. The Earth experiences more heat from the Sun when it's furthest away from it. 6. It would explain how the inertia satellites lose to centrifugal force is replenished. 7. It would explain why polar orbits are so unpredictable. 8. It explains long-term weather changes. 9. It would explain some pretty dramatic periodic changes that the Earth has experienced as evidenced in its geologic record. And 10. It would explain how Mars is able to periodically maintain a rain-bearing atmosphere. I came up with this concept when I was 23. At that age, I had already had some degree of success in writing nonfiction. Against the advice of my editor, I decided to try my hand at fiction, and I came up with a story of New Atlantis. The story was a fun look at the idea of what would have happened if the story of Atlantis had taken place in modern times. The story involved space travel, and I wanted it to be feasible, so I gave some very serious consideration to the aspects of high-speed travel. Well, the book never got published, but this video conveys the end result of that consideration. In 1984, I was watching the Nova television show on PBS. A professor, Walter Alvarez from Berkeley, was speaking on the show. He was looking at evidence in the Earth's geologic record that shows that the Earth has gone through some pretty dramatic changes in regular intervals, and he was asking why. I thought, I have the answer to that question, so I sent him a 4-page summary of my concept entitled The Course of a Galactic Year. Shortly thereafter, I received the paper back from Dr. Alvarez with a post-it note attached saying, "Dear Mr. Wagner, thanks for your letter, but I cannot comment on your theory as I'm not an astrophysicist." Next, I sent it to Omni magazine, where I'd read an article pertaining to this topic. They said no one on their staff was qualified to evaluate the theory. I sent it several other places thereafter and always got a similar response, so I wound up sitting on the theory for the next 25 years. A couple of years ago, I decided to teach myself computer animation and to make this video. I figured if it turns out not to have any merit, it's at least been a fun project. But if it turns out that it does have merit, it'd be a real shame for me to pass from this life without having left this behind.